name is Kevin Hofmann. I'm an automation specialist at Eli Lilly and Company. My job responsibilities include starting up processes and maintaining them later. And over the years, I've started up several different processes ranging from distillation columns for solvent recovery to bead coating processes that coat beads for capsule filling. And I've also started up and currently I'm starting up a process for insulin manufacturing where we will formulate insulin and then fill 3 milliliter cartridges. What I'm going to speak about today is fuzzy logic and why we don't see it more often used in process control. In order to understand this, we must first understand what fuzzy logic is. I'll cover a very brief history of fuzzy logic. I'll give some examples of 2 different process applications that will demonstrate how fuzzy logic is created and how it can be used to control processes, and I'll make some comparisons to conventional PID control. Fuzzy logic is a branch of artificial intelligence. This is primarily due to the fact that the logic is reasoning-based. Fuzzy logic uses words, not numbers, to accomplish control. When we think of digital logic, we think of true and false, a 1 or a 0. Fuzzy logic, on the other hand, uses linguistic rules to describe varying degrees of trueness or falseness. Inputs and outputs can be some value between true and false. That degree of truth can be used to control the process. The term fuzzy logic was coined by Lofty A. Zeta, a professor of systems theory at the University of California, Berkeley, in 1965. At that time, many of his peers criticized him for imprecise thinking. Since that time, it's been studied and become a more acceptable theory. It has been used in products and items like commercial appliances. It was used in 1988 to run the Sendai subway system in Japan, and yes, fuzzy logic has been developed and used in PLCs. However, it is used much less than first principle models, like traditional control systems that use PID controllers. Here's an overview of a fuzzy logic system. Inputs are fed into the fuzzy logic system where fuzzification takes place. Fuzzification is the process of converting the inputs to linguistic variables, applying linguistic rules to them in an inference mechanism, then defuzzifying the information to provide a crisp output to some controlled device or process. Here's a simple example of a fuzzy logic application that uses a temperature input and a cooling fan for the output. There are several steps that are followed to implement a fuzzy logic controller. The first step is defining the linguistic variables, both input and output. In this case, the input variables are defined as cold, normal, and hot. The output linguistic variables are defined as slow, medium, and fast. Notice how the variables are imprecise values. They aren't defined as a specific temperature for the input temperature or a specific speed for the output to the fan. This is part of the characteristics of fuzzy logic and why Zeta was criticized for his theory. The next step is to define the linguistic terms or rules that are applied to the system. Fuzzy logic terms are presented as if-then rules. In this example, Rule 1 is if hot, then fast. Rule 2 is if warm, then medium, and Rule 3 is if cold, then slow. These statements can be much more complex than this if the process requires it. Fuzzy sets are placed into membership functions that are created from the variables and rules for the inputs and outputs of a system. You can see these membership functions are created using triangles. However, there are various shapes that can be used, such as trapezoid, Gaussian, sigmoid, or user-definable. Notice that the range of the y-axis is 0% to 100% for both the input and output functions. Also note that the peaks of the triangles are at 100%. This is in relation to the truth of the fuzzy condition. The peak is where the rule becomes completely true for that particular member, and the base of the triangle is where the member becomes completely false. All the points between completely true and completely false are the member's degree of fulfillment. The members within each set overlap at some point along the x-axis. This is important because if the members don't overlap, then there won't be a fuzzy condition. Each member would either be completely true or completely false. Now that we've created a fuzzy logic system, we can infer from a given input what an output will be. The inference mechanism is a way of computing output values from input values that are based on the rules applied to the membership functions. In the example, a temperature of 52 degrees on the x-axis of the input member assumed at the time of the inference. If a vertical line is drawn from the 52-degree reference on the x-axis, it intersects lines on both the cold and normal conditions. The normal is intersected at approximately 30% horizontally from the y-axis, and the cold is intersected at approximately 60% horizontally from the y-axis. These are considered the degree of fulfillment for each function. The degree of fulfillment can then be shown to intersect with points on the output member function as well. The shaded areas represent the degree of fulfillment for that output member within the function. The area under the members can be used to calculate the centroid average, providing a crisp output value from the fuzzy logic, in this case, approximately 44%. The centroid average is the sum of each rule's outcome grade times its actual output data. Since we now have a basic understanding how to develop a fuzzy logic controller, let's take a look at a system that is a bit more complex. This egg cleaning system is designed to measure the dirt on eggs and adjust the water flow rate for washing to compensate for the amount of dirt. You can see we have an input sensor to measure egg dirt and an output to operate a flow control valve for water that washes the eggs. As shown above, rules are developed to provide control to change the position of the water valve. There are 2 input and 1 output member functions for this controller. In this example, the trapezoid shape was used for the membership functions. What that shows us is that the members are true or false on x-axis points at more than 1 input value. One input is egg dirt, which has members of low, acceptable, and high. The other input is flow rate, which has only 2 members, low and high. The output is described as position change, and it can move either positive or negative from 0 based on the input reasoning from our rules. This diagram shows the requirements to make an output decision based on the 2 inputs to the fuzzy system. As can be seen, a great deal of thought goes into creating this controller. The input membership functions were created, the 5 rules are applied, and an output position move is determined. We can see that in the rules that there was an AND operator used in making decisions. There are other operators that can be used for these rules, such as the OR and the NOT operators. We can see from this that with more inputs to a system, there will also be greater complexity. The resulting output from a slightly lower than acceptable value of egg dirt will provide a slight move of the valve in the negative direction. Conversely, if the egg dirt was not completely acceptable and not completely high with the same current value of flow, the controller would move our valve in the positive direction by some value. Fuzzy logic can be used to control a process, but in many cases, 90% or more, it still makes sense to use traditional PID control for a process. Fuzzy logic takes a strong understanding of the process and the ability to translate the process to variables and rules that are fuzzy or imprecise. In a highly regulated industry like the pharmaceutical industry where I work, you can see why fuzzy logic might be difficult to validate since it is based on imprecise linguistic terms. FDA and other agencies are very serious about how a process behaves under any condition, and it must be understandable and repeatable. The process must be qualified and validated on known facts about its operation. It's a bit more difficult to explain the operation of a fuzzy logic system than a traditional PID control loop. Controls engineers are simply used to the PID control algorithms and they're familiar with them. PID control is easier to implement in most cases. However, if controls engineers use fuzzy logic and become more familiar with it, it will continue to increase in its use. There are tools available for implementing fuzzy logic that have improved the PLC programmer's ability to use it. As tools continue to evolve, fuzzy logic may be seen in greater use for process control.